Now, hopefully, the beginning study of infinity is not too mind-blowing, that as we work with infinity, it can get complex, but if we take it slowly enough, we can understand what's happening. Now, I have some interesting pictures here. The pictures of what look like worlds all going together in a spiral. Of course, the spiral moves away from you as it goes, so imagine that it could be there an infinite number of times. And we'll actually see something similar to this in a future lesson about a month from now, or maybe a little less. We'll see. The other picture of the boy taking a picture of himself, and with what appears to be an infinite number of reflections. While it looks very complex, maybe you've seen this kind of thing. You can take a picture like this simply by using 3 mirrors. And believe it or not, it works. They're in an equilateral triangle shape, and at the right angle, you believe that you could see yourself an infinite number of times inside of these things. It's rather surprising. Now, if we look at infinity, I'm going to go back to the homework from yesterday and start with hotel cardinality, number 16 from the book. When you're working with hotel cardinality, the whole gist of this, well, it's taken off of Hotel California. It's an album or a song by the Beach Boys back in the 1960s, so it's pretty old, but the authors apparently liked it, so he's kind of playing with that. With hotel cardinality, there's an infinite number of rooms, but you're only allowed to have one person in each room. And that's how we're starting. Now, the second thing, of course, that I didn't mention is that hotel cardinality is full. There's one person in each room. Now, question number 16 asks you if you came up to hotel cardinality. Or let's put it this way. If you were the night manager there and you knew all of the rooms were full, infinite number of people, one per room in an infinite number of rooms, and someone comes in and says, please give me a room. I've been traveling so long and I'm tired. Can you find a way to give me a room? Well, you scratch your head for a while and figure, well, how could I do this? How could you find room for one person? Well, we know from trying to compare the cardinality of the whole numbers to the naturals, that putting one more person into infinity is entirely possible. Maybe all we need to do is to shift it down, shift each person down one room. So, excuse me, you get on the loudspeaker, the PA system in the hotel, and you announce to every guest that you have that they should look at their room number, add 1 to it, and move to that room, that new room, which is increased by 1 from where they're staying. All of them move down 1 room, and now the first room is available. So you actually can do this. If you try to put them on the end, you really can't tell them a particular room number to go to. After all, if you wanted to say, well, go to the end of infinity, well, infinity never stops. If you give them a room number, that one's full and someone's there. So you have to shift everything, tell them all to move up 1 room, and the first room is available. From this number 16, we learn that infinity plus 1 is still equal to infinity. Now, in this case, the plus 1, it was literally 1 person, but think of this figuratively as in let 1 represent any finite number. So, like in question number 17, it comes and says, well, what if 2 people come up? Well, then you simply tell everyone to add 2 to their room number and it moves down. If you had a bus come with, and it'd be a really big bus, but 1,000 people in it, well, you tell everyone to add 1,000 to the room number, move down, and the first thousands are available for someone to move into. So it's not too hard. Infinity plus any finite number, the cardinality will always still be infinity. Now, in number 18, we're in that same scenario again. The hotel is full. You're the night manager. But now an even bigger bus comes. And this bus is from the Infinite Life Insurance Company. And it comes and it has an infinite number of people on. How do you fit them in? You can't tell everyone, okay, go move down an infinite number of rooms, because they'd be moving all night. They would never find a room. No one would get any sleep. Everybody would want their money back and you would go bankrupt. Well, is there a way to get an infinite number of people into a full hotel cardinality? Well, we think we should, because after all, when we worked with the integers, we looked at it as having a positive infinity and a negative infinity, that there's like two infinities, and we could still get it into the cardinality of the natural numbers. So we think we should. Well, how could we do this? What would be the ways of doing this? Well, one way to do this would be to tell everyone to look at their room number and multiply their room number by 2, then move to that new room number. Room 1 would go to room 2, room 2 would go to room 4, room 3 would move to room 6, and 4 would go to 8, 5 would go to 10, 6 would go to 12. Well, we notice then that when we do this, because we're multiplying it by 2, all of the rooms that are even are full. And the people that were in rooms 1, 3, and 5, well, they moved to an even number room. So all of the odd numbered rooms are available. How many odd numbered rooms are there in Hotel Infinity? An infinite number. So you can tell the people on the bus from Infinite Life that has an infinite number of people, each of them should just go to the next available odd numbered room, and everyone gets in, and everyone's happy. And you increased your profit margin by a significant amount. Now, from number 18, then, we learned that infinity plus infinity still equals infinity. Now, saying infinity plus infinity equals infinity isn't the best way to describe it, but it's a good way to connect it with existing math that you're well aware of. Now, if we work with this, we go a little bit further and say, well, okay, Hotel Infinity is full again. Now, an infinite number of buses come up. And on each bus, there's an infinite number of people. Well, how do we do this? Well, we don't really want to tell everyone an infinite number of times to multiply your room by 2 and move to that room, and then multiply it by 2 and move to a room. Again, no one gets any sleep, and people are upset. How could you do this? Well, this is a little bit more complex, and this would never be on any quiz or test. But the idea would be that the prime numbers are all, except for the multiples of 2, they're all odd numbers. And so the first step in it is to tell everyone in their room to go and look at their room number and multiply it by 2 and go there. Now they can stay there. Now, there's all of the odd numbers are available. Now what you do is you tell everyone that is in, like the first bus, you tell them that they are the multiples of 3, or not the multiples of 3, the powers of 3. We're going to start with 3 as the first prime number. So the first person on that bus is 3 to the first power. They go to room 3. The second person on the bus is 3 to the second power. They go to room 9. The next person is on that bus is 3 to the third power, which is 27. They go to that room. The next bus is 3 to the fourth power. The fourth person on that bus is 3 to the fourth power, so they go to room 91. So for each person, you increase the exponent by 1, and they go into that room. The next bus, you go to the next prime number, 5. 5 to the first, 5 squared, 5 to the third, 5 to the fourth, 5 to the fifth. And you do that for the next bus that comes. They are the next prime number, in this case 7. 7 to the first, 7 to the second, 7 to the third, 7 to the fourth, and so on. So there's an infinite number of prime numbers and an infinite number of powers for each prime number, and they will overlap. After all, if you have 3 squared or 3 to the third, you can't factor it into 5 in any way. So there will be no overlap of rooms. Everyone that's on one of the new buses gets a room, and in fact there will be some rooms empty. For example, well, actually there will be a few rooms that are not empty, but not many. Now, that's an example of looking at infinity times infinity equals infinity still. So infinity is very large, and this would be a little bit like trying to compare the cardinality of the rational numbers with the cardinality of the naturals. was an infinite number of infinities inside of the rational numbers, and it all fit inside, had the same cardinality of the infinity of the naturals. Now, question number 21 in the homework says, suppose you have a set. If you remove some of the things from the set, will the collection remaining always contain fewer things than in its original set? Well, if you're working in the finite, of course, yes, that will always be the case. If you have 29 objects in a set and you remove 2, 27 is the remainder. That's smaller than 29. But if you have an infinite number in the set, all of the natural numbers, for example, and you take out, say you take out 2, 4, 6, and 8. Well, once you remove that, the original set is all the naturals minus those, but it's still infinite. So infinity minus a finite number is still infinity. In fact, you can even take out an infinite number of things. With this, for example, you could take out all of the multiples of 10 from the natural numbers. All the multiples of 10 is an infinite number, and when you take them out, the naturals are still infinite in size. So when we work with this, we find that infinity minus a finite number is still equal to infinity, and infinity minus an infinite number, another infinity, is still infinite. And maybe this could also just be seen by looking at the cardinality of the rational numbers. If you take out one of the infinities of that infinite number of infinities, you still have infinity. Now, number 22 goes on to say, okay, now describe a collection of numbers you could remove from the set of natural numbers so that the set remains, has fewer than before. So, well, we just said that infinity minus infinity still leaves infinity. How could you do this? Well, there is one way, and there's different ways to look at it. The one is, well, what if you removed, for example, if you have the natural numbers, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 through infinity. Well, what if you removed the infinity from 5 through infinity? 5, 6, 7, 8, 9, 10, 11, the whole way out to the end of infinity. If you remove that infinity, you're left simply with 1, 2, 3, and 4 in the original set. And that would be finite. So it's possible under certain situations that infinity minus infinity can equal a finite number. The other way of thinking about it is to say, well, if I'm going to try and do this and have it be finite, well, then I need to remove the infinite part of the set. Leave in just a couple, even maybe just leave the first 1,000 in, but then remove the rest of the infinities, which would include the infinite number of infinities of the rational numbers. So if that didn't make sense, don't worry about it. But the concept is you have to kind of be clear as to what you're removing. If infinity can hold an infinite number of infinities, if you just take out a couple of them, well, there's still an infinite number left. But if you remove all of the infinities, then you're left with a finite number. Here's a cartoon. Hopefully you can read it there. And Professor Herman stopped when he heard the unmistakable thud. Another brain had imploded. Well, maybe you're starting to feel that way about the study of infinity. I'm hoping not, but keep it together. We'll get through this, and hopefully your brain will not implode. Today's lesson moves on to the missing member, section 3.3 of the textbook. And please do read the textbook. It is helpful, but what I give hopefully gives better preparation for it, and hopefully you can understand things better because of this video. Now, you may not agree with the fact that infinity is interesting. Some students think it's a little bit of torture, but hopefully it's surprising and not too tortuous. Now, Galileo came up with a paradox, and Galileo said, now, which has more points in it? a line segment from 0 to 1, including 0 and 1, or a line segment from 0 to 2, including 0 and 2. Well, when we look at it, obviously, wow, there must be twice the number of dots in 0 to 2 as there are in 0 to 1. For every point there is from 0 to 1, that takes care of the 0 to 1 to bottom, but then nothing corresponds from the 1 to 2. Oh, but wait a second. We go back and say, we did something like this. We kind of had two infinities when we were working with the integers and comparing it to the naturals, and we said we could do that. Well, maybe that means we can do that here too. Well, if we wanted to prove that these two had the same number of points in it, after all, a line like this, like the real numbers, has an infinite number of points from 0 to 1 and an infinite points from 0 to 2. And if infinity is all the same size, the same cardinality, then they really should have the same number of points, regardless of how long that line is. Well, one way to look at this is if we drew a line. I kind of missed one there, but that's because I've got a bad graphics program here. PowerPoint's great for presentation, but it's not real accurate. That's supposed to go through point 2 of the bottom line and point 1 of the top line, and it just extended it beyond. And then it did the same thing for 0 and 0, and extended it up. And we look up here and say, well, yeah, at this point up here, it looks like that's kind of the point where those two lines come together. Now, I could take a line from that point and draw it down through, well, I guess it would be 1/2 of the top line down to 1 of the bottom line. And if I keep drawing from that point a straight line down to the bottom line, every time I do this, I come up with a line that goes through exactly 1 point of the top line from the line segment from 0 to 1, and it also goes through exactly 1 point of the bottom line. Now, if I did this an infinite number of times, I would get the same thing. No numbers are going to overlap at all. Even when you get incredibly close to 0 on the top line, you say, well, it's twice as far out. Well, you can have that distance in on the bottom number, but then even on the top, you have a 0 and another point, and you can always find the difference halfway between that point. So as we do that, we realize if we did this an infinite number of times, there would be a 1-to-1 correspondence, and that would mean that there are the same number of points in the line segment from 0 to 1 as there are in the line segment from 0 to 2. It appears to be twice as long, but they actually have the same number of points. The cardinality of both lines is exactly the same. Now, what if we removed the points at 0 and 1 of the first line, and then left them on in the line segment from 0 to 2? Now, I left the little dot up there to see it. If we're going to draw a line from 2 through 1, well, now it actually has to be the point right beside 1, not including 1, and a line from 0 down the bottom up through the point right beside 0, not including 0, on the top. Well, this kind of moves that blue dot. Draw another one here that's red. That would be the point that the things would now come. The lines would go through. So it has moved down and a little bit to the right. So then I can come in and start drawing these same lines. And as I keep going, I will do this an infinite number of times, at least theoretically, and say that for each line, it intersects the top and the bottom lines only at 1 point each time. So even if we remove the point 0 and 1, there's still an infinite number. So the line segment between 0 and 1, not including 0 and 1, has the same number of points as does the line segment from 0 to 2, including 0 and 2. Well, if you believe the first one, and it made sense, this isn't too much harder to grasp. But let's use this. Now, what if we compared this same line segment from 0 to 1, not including 0 and 1, with the entire real number line? Does the real number line have more points than just a line segment from 0 to 1 that is of the real numbers too? Or would they have the same cardinality? This is tricky. Now, we usually view line segments as being straight, but if I took this line segment from 0 to 1, I could bend it, right? And it would still be a line segment. In fact, I could bend it several times. Well, I could bend it, but I could also kind of smooth it into a curve if I really wanted. And it would still be all the points, an infinite number of points between 0 and 1, not including 0 and 1. Well, then I could take the shape and bend it one way. It kind of looks a little bit like a smile, doesn't it? And then I could keep bending those 2 points closer and closer together. Well, what if I kind of made the shape in a circle, then overlapped that hole at 0 and that hole at 1 into a circle that would appear to have just a hole at the top? There's 2 holes there, but they're overlapping each other, so you don't see the second hole. Well, it's a circle, right? So if we compare the line segment from 0 to 1, it's like comparing that line segment to the entire reals. It's kind of like comparing a circle with a hole at the top to the real number line. So now we have this line segment from 0 to 1 that's rolled into a circle and the real number line. If we wanted to show a one-to-one correspondence with this, well, we need to have each point from the almost complete circle compared to a point on the number line. Well, since the very top circle is not a point, we can start a line there and draw one, for example, straight down. So that would correspond the 1 point at the very bottom of the circle to 0. Now, we can continue to move that line out. We can start again at the point where there is no point at the top and move over to the next. Well, this is a bigger jump, but you can move very, very small increments. And if you imagine it as a line, you keep moving it over, keep drawing lines more and more to the left. We see that we could actually make a one-to-one pairing with all the numbers on the negative side of the real number line, because it would keep going over, and the further and further left we go, it still goes through 1 point of the circle to 1 point of the real number line. In fact, even if you did from the hole to the very next point, right next to it, we imagine that could go down and touch the negative infinity down there. Go down and touch, if there was a last number, touch the last number. Well, if we can do that on the negative side, we can also do the same thing on the positive side. And as we do that, every time we draw a line, it touches 1 point of the circle and 1 point of the real number line. And again, the very last one, if you do the very last point there, we imagine it could go out to the positive infinity out there, if there was such a number. So, what does that tell us? Well, we did a line segment from 0 to 1. And that means that there's as many points in the real number line from 0 to 1, not even including 0 and 1, and the entire real number line. Well, that's a little surprising, but we just proved it. That also means that a circle, if we had a circle, we had one, it just missed the top point. So we could imagine just filling in that top point, and it would still be the same cardinality, because infinity plus one more point is still going to be infinity. And so the cardinality of the number of points in a circle is the same as the number of points in the real number line. The cardinalities are equal. And in fact, restating it again, it's the same as a line segment between 0 and 1. And going back to the first point, well, that means any line segment, because I could do the same thing with all the points between 1 and 2, right? I could do all of this, the same thing with the points between 0 and 1/2. I could even do a line segment that's short, like from 0 to 0.0001. And I could do the same thing with that. The circle would be very small, of course, but I could do it. So that means any number line length. So it would also be true for a line segment between 0 and this number, and even what we think of as lengths shorter than that. Kind of mind-blowing, huh? Have a headache yet? Remember dodgeball. Take a short breather here. Dodgeball, if you don't remember it, I'm not going to take a long time to explain it, but player 1 goes first, fills in X's and O's at the top, and then player 2 does the first one, and then player 1 goes again in the second row, and player 1 tries to match what player 2 will write, and player 2 is always trying to write a pattern that does not exist for anything that player 1 writes the entire game. Well, you can review that from the first chapter if you forget it. But we said, well, if we do the diagonal, if we look at the first one of the first box of the first row and do the opposite of that, then it can't equal the first row. So player 2 is guaranteed not to match row 1 because he did the opposite of it. If it was an X, he wrote an O. If it was an O, he wrote an X. And then we did the same thing for row 2. Whatever player 1 wrote there, player 2 did the opposite of that. Whatever player wrote in the third one of the third row, third column of the third row, player 2 did the opposite of that. And the opposite of the fourth, player 2 did the opposite. The player 1 did the fifth of the fifth, and player 2 did the opposite. The sixth of the sixth, player 2 does the opposite. Because he did the opposite of that diagonal, it can't be any of those rows. Player 2's first block can't match the first row. Player 2's second block can't match the second row. The third block cannot match player 1's third row. The fourth cannot match the fourth row. The fifth cannot match the fifth row of player 1. And player 2's block 6 cannot match the sixth one of player 1's, the sixth row of player 1 writes. So player 2 is guaranteed to win. Now, could we change the rules to ensure that player 1 wins? Sure, and that would be if you let player 1 go a seventh row, go one more time, and then he could write the patterns for the first 6, and that player 2 has, and he would win, obviously. Well, that means that if there are more columns than there are rows, player 1 was guaranteed to win. But if they have the same number, if they have the same number of rows as columns, if there are 6 columns and 6 rows, then player 2 always wins. If it's a 4x4, as long as there's 4 rows and 4 columns, player 2 will win. If there's 120 columns and 120 rows, player 2 will win. So even if there's an infinite number of columns and an infinite number of rows, if you could play it, player 2 would win. Now, is there a set with a cardinality larger than the natural numbers? Just a quick review. We first compared it with the natural numbers to learn the notation. And we set up like this. Then we did the whole numbers, and we said, oh my, with that same setup it didn't work. So we shifted it, and then it worked. And it had the same cardinality. With the integers, we went through it and said, oh, well, let's do this. That one is paired with 0, and then the next even one goes to the next odd integer. And of the naturals, the next odd number is paired with the next positive integer. And we said that you can do this an infinite number of times, so it has the same cardinality. And we did the rationals, and we set the rationals up like this, did that square spiral, and each time you crossed a number, a rational, you paired that with the next natural number, and of course then the cardinality was the same. Now, what about the real numbers? Well, we need to use dodgeball to figure this out. Now, player 1 and 2, same game that we just reviewed. We're interested in the diagonal, just as before. Now, with this section where we did the line segment from 0 to 1, well, that was preparing us for this. What we're going to do is fill in, now I'm just showing you the first 6 digits of the number, but we're going to pick an infinite number of numbers between 0 and 1, not including 0 and 1. and list all of these numbers. So we have to kind of imagine what's happening here. That each number that I have across is infinitely long, and there's an infinite number of rows, not just 1, 2, 3, 4, 5, 6, but down through infinity. There's an infinite number of rows down. Now, what we do, we want to do a one-to-one correspondence. So the natural thing is to set up, of the natural numbers, pair 1 with the first number there in the first row. Pair 2 with a number in the second row. Pair 3 with the third row, 4 with the fourth row, 5 with the fifth row, down through infinity. So we think we have an infinite number. So we get someone who can write incredibly fast. And they write out an infinite list like this. Now, George Cantor developed this argument, and it's referred to as Cantor's diagonalization argument. It uses the same diagonal as we did with dodgeball. Now, in dodgeball, you said, well, it's X's and O's. Whatever the player 1 writes, player 2 writes the opposite of it. If he writes an X, well, the opposite is an O. If he writes an O, the opposite is an X. Well, what's the opposite? If you look at the first digit in the first number, in first column, first row, it's a 5. Well, what's the opposite of a 5? Well, in math, the opposite is -5, and that doesn't work. We can't do that. So you have to think about this. What could we use that would be the opposite of 5? Well, you know, there is a way to do this. And Cantor said, we can always do the opposite. What we do is we look at that diagonal, and the first digit, like there, the number 5, we look at the diagonal, and then we say, okay, if that digit is a 2, then I'm going to write a 2. I'm going to write a 4. Okay, so he just picks that. Well, now, the thing is, the rest of them could be a 1, a 3, 4, 5, 6, 7, 8, 9, even a 0. Well, what would be the opposite of that? And Cantor said, oh, well, that's pretty simple, actually. As the number is either going to be 2 or it's not going to be 2. Hopefully that makes sense. The number you're looking at, it's either 2 or it's not 2. So he found 2 cases. And it says, if it's 2, I'm going to write a 4 in my number. But if it's not 2, anything but a 2, then I'm going to write 2 down. So I always have the opposite of it. And he just used 4. He just picked that because it works. I mean, not that it's only one number that works, but it works fine. So he needed a number, he used 4. So in this case, we look at the first one. Now, again, the number that we get down here as player 2, it's going to be between 0 and 1. So it's 0 point, and then as we fill in the rest of this with the natural number, it'll work. What's the opposite of a 5? Well, we look at it and say, okay, is that a 2? Well, no, it's not a 2. It's a 5. It's not 2, so then I write a 2 in my number. The next one is a 2. Okay, it is a 2, so if it is a 2, according to Cantor, then I write a 4. So I put 4 down there. The third of the third row, third column, is an 8. Well, that's not 2. Well, if it's not 2, then I write 2. The fourth of the fourth is a 3. Well, again, that's not 2, so I write a 2. The fifth of the fifth is a 1. Well, that's not 2, so I write a 2. The sixth of the sixth, oh, that is a 2. So I write 4 in there. Now, we do this an infinite number of times. We do the 7th of the 7th row, 8th column, 8th row, the 9th of the 9th, the 10th of the 10th, the 11th of the 11th, on through infinity. And by the same logic of dodgeball, because you did the diagonal, the number that you get on the bottom will not be on the list. The same as the first 2, it can't be the very first one, the first row that player 1 wrote, because that starts with a 5. As long as there's as long as there's the same number of columns and rows, this diagonalization argument works. Are there the same number of columns and rows? Yes, there's an infinite number of columns and an infinite number of rows. Exactly the same size, the same cardinality. So when we get done, our number between 0 and 1 will be infinitely long. But it will be a number that's not in the list. As we say, well, what if it was the 50th one? Well, that was the opposite of the 50th column in the 50th row. So it can't be the 50th one, the 50th one on the list, on the row. What if it was the 150,000th? Well, that one was the 150,000th column, 150,000th row. It's the opposite of that, so it can't be the 150,000th row. We go through and do this an infinite number of times. It can't be any of them. So we found a number that's not on the list. That's like going through having two ping pong balls, two infinite-sized ping pong barrels with an infinite number of ping pong balls in them, and you do a one-to-one pairing, and you finish the one barrel, and you realize there's still another one in the other barrel. So that barrel had more in it, had a greater cardinality than the other one. I say, well, but Greg, that's just one. Well, let's look at this again. This number that we got, what if we put it at top and say, oh, we just missed one. It was a mistake. So let's put this number on top and do this again. Now everything's going to shift over. We're going to now look at this diagonal. It still has an infinite number of rows and an infinite number of columns. But again, it's the first one now is a 2. Well, if it is a 2, then I write 4. Then the next one is 8, and that is not 2, so I write 2. The next one is 3. It's not 2, so I write 2. The next one is 9. It's not 2, so I write 2. The next one is 2, so I write 4. The next one is 2, so I write 4 again. And I keep going. Now this one won't be on the list. And I can do this an infinite number of times, and each time I'll find a number. So that means that there must be more reals between 0 and 1 than there are the naturals. Wow, that's kind of strange, isn't it? It's like we go into the barrel, and once we empty the barrel of the naturals, we realize that there's an infinite number of numbers still inside of there. Now, this is not good math concept, but if it helps you understand it better, you could say, well, we're just using the reals between 0 and 1. Well, what about the reals between 1 and 2 and 3 and 4? We could do this for each of those. We'd have an infinite number of barrels to compare, but we get at least one number that's not in the reals between 0 and 1, and then we get at least one that's not in the reals or the natural in the real number list from 1 to 2, and then another one for 2 to 3, and another one for 3 to 4, and another one for 4 to 5. And so there'd be an infinite number of these marbles that were missed. So that means that the reals have a greater cardinality than the natural numbers do. Wow. Do you feel like your brain's imploded at this point? It actually does work this way. And you can read through the book, and maybe that can help a little bit too if it seems hard to swallow, hard to believe. Now, at least we're now to the end. You can let your brain rest a little bit. Here is the homework. It's also a course on Moodle, and I'm asking you to send in a photo of questions. The list is there, to email them to me. This gives me a chance to monitor and make sure you're understanding how things are working with Infinity. Again, if you have questions, you can always contact me by email, or we can set up a Skype call. So have a good day.